It's my pleasure to introduce Biagio Cosenza. Biagio got his PhD at the University of Innsbruck in the Thomas Faringes group. His expertise in traditional compilers, but he's slightly moved towards heterogeneous GPU programming, right? He also spent a lot of time in Germany at Technical University of Berlin, and now is a professor at the University of Salerno and trainer on the Intel SQL and WNAPI technology. So join me and thank Biagio to here. And Biagio, the stage is yours.
Thank you very much. Thank you very much for the introduction. So good morning, everyone. So it's a great pleasure for me to be here. Thank you, Flavio, for the organization. Today, I will give you an introduction to the topic of GPU programming fundamentals. So um, just to be clear, I will provide you two ways to run all the code I show you. So one is, and I will show you all the command line command you need to run it on Cineca. But I also prepared a web page with link to Compiler Explorer. Do you know Compiler Explorer? How many of you know Compiler Explorer? Ah, good, good. So it's just a browser. So you go on a link. Actually, you can right now open your browser, open this link here. The link is also on the slide if you can download the slide. Okay. Then there is a web page for each code I'm showing you. There is both a file on a GitHub and a link to the Compiler Explorer. Of course, Compiler Explorer will work on CPU, not on GPU, but it's good if you want to make some practice. Okay. So I will give you a very brief introduction to how modern GPU are done, the historical context, and how modern GPU are made. Very brief introduction on how to set up all the code you see here in Cineca. And then I will provide you mainly three parts. First part is about the fundamental of SQL programming. So we will use SQL, which is a programming model, portable programming model, which works on all the GPUs from NVIDIA, Intel, and AMD. So we'll provide, first of all, the foundation, the basics, Q and parallel for parallelism. Later, I will show you more advanced topic. And at the very, very end, I will focus on what I call beyond SQL. Those are not on the standard. Those are extensions that are useful for AI or other kind of extension to program, for instance, cluster of GPU. So this is more advanced part at the very end. To show you some research on this topic. So let's start with an historical perspective. What is a GPU, right? The name is graphic processing unit. So it comes from graphics. And the idea is that what we are doing with GPU is to use a device that was designed for graphics and to use for general purpose computation. So, but why they are so powerful? No, GPU were designed to support what is called the rasterization pipeline. So if you had a computer graphics course, you know what I'm talking about. So the idea is that when you have a video game or any rendering program, you need to process many vertex, then you need to process many triangles, and then you need to process many pixels. Okay. The idea is that the computation is organized in stage, and the good point is that this hardware, which was indeed really a domain-specific hardware, was very specialized for this kind of workload, was exploiting properties of the program to make it faster. And the first obvious property is that each vertex is independent of each other, each triangle is independent of each other, each pixel is independent of each other. So this is a perfect case for parallelism. And there are also other interesting features of GPU, as they were designed. If you see, this is a Riva TNT2. Do you know this one? You are too young for this. was a very popular gaming GPU, and was so good because it had texture cache and vector cache. So it has, on one end, weak memory model, relaxed memory model, but support for very small but very fast local memory. Okay, this is the idea, and the idea is that the other interesting idea was that you had this rasterization pipeline, but some specific part of the pipeline, at the time, it was just vertex and fragment shader, but later then it changed. Very specific part of this pipeline could be programmed. So you were, for instance, doing something like that. So you had a program written in a shading language. This is OpenGL shading language. And you, in this case, this is a pixel shader. Particularly, you just write how to calculate one color. What is implicit here is that each pixel calculation is independent of each other. So, and you get a picture like that, okay? Then later we had the evolution, which was the early steps of GPU. So the idea to use those GPU to solve problem, not just rendering. And for instance, and this was very popular long time ago, even though GPU were not yet ready. For instance, they were not yet supporting 14-point IEEE standard. But what you can do, you could do at the time, and you can still do now, is to map, for instance, array as a texture. Then your shader become your kernel part, the computational part, and you can, for instance, write a SaxPy application. SaxPy is very simple code we'll see very often today. And this is how you write in a shading language. For a long time, this was the way to do it, until we had modern, let's say, GPU programming model providing support for general purpose programming models. So we had one of the first was Brooks. Then we had CUDA from NVIDIA. We have, as of today, we have many proprietary programming model, which means they are being designed by the vendor. And so we have CUDA by NVIDIA, we have ROCm HIP by AMD, and we have Level 0 by Intel. Okay, those are rather low level. You have a very much high control of the hardware. They are not portable. Okay, if you write your code in CUDA, it's not portable to another device, and depending on the feature you use, may even not be portable between different NVIDIA architecture and generation. On the other hand, we have more general purpose programming model, mostly designed by the Kronos group, which is an industry group designing standard, where there are different companies sitting on the table, try to find a common language. And out of this, we have OpenCL and SQL, which is the one we will see today. So let's say this is a historical perspective, but what do we have now? Today we have GPU in all the faster computer in the world. If we have, for instance, AMD Instinct MI250 is the one you found on Frontier and on Lumi, or Intel Max 1100 you find in Aurora, in Chicago. And we also have Leonardo, number 7 from Cineca with NVIDIA A100. So different, but still many things are the same. They all have exposed massive parallelism. They are all organized in more, what I will say, compute units. Be careful with the language. So I will try to use vendor agnostic language. So Kronos call it compute unit, but if you go on NVIDIA, you will see streaming multiprocessor. If you go on AMD, they are called GCD, graphics compute die. And on Intel, they are called tile, okay, tile or stack, depending on the different version, okay. And we will see there are many things very similar. So I'm trying to show you what is similar between all the GPUs. And so if we do HPC today, we have to do this. You know, we need to know about how modern GPU are designed, so how different components work, and the design, which is today more oriented to NUMA-like design. So I will give you a very quick overview because then I want to show the code. So just a very quick overview of the main feature of modern GPU. That's a very long topic. We could give a lecture, a whole course about how GPU are designed, but I will just focus on 3 points so that then we start to see the code. So first of all, the platform model. So obviously GPU is a separate accelerator. Actually, there are exceptions, but let's put it this way. So we have a GPU which is separated from the CPU. So at some point, you need to move the data. So you have your program on your CPU, you need to move the data to the GPU, and then you gather the results and go back, okay? Those are typical steps you do with a GPU. There are, let's say, exception, memory may be shared, but even there you need, there are cache coherence problem and so forth. So for now, let's start with a more generic picture, okay? So what does it mean? That we have, on one end, we have the host, which is the CPU, and on the other hand, we have one or more devices. Here I wrote OpenCL or SQL device. This is still the terminology used by Kronos, okay? One or more devices means one or more GPUs. So if you are familiar with Leonardo machine in Cineca, you will see later, you see 4 devices, okay, which is one device is one of the GPU, okay? Each device has more compute unit. If we think about Cineca hardware, where we have an A100, the computing unit are the streaming multiprocessor. And each computing unit has more processing elements. Okay, this is also terminology we will see may change on NVIDIA is a CUDA thread practically. And more or less this is the same. This is terminology. It maps on all the hardware I show you. Okay. Regarding the execution model, okay, even the execution model, the idea is that we have a lot of parallels. So, and this parallel is organized in work group. Why work group? Because the work group is like a bunch of work which will run on a compute unit. Okay. On the slide, you will find the notes. If you are familiar with CUDA, maybe you are confused by the terminology. I always put the note. On NVIDIA is a block. Okay. And so the idea is that we have a lot of work, which is this work items. The work items are organized in work group, okay? And each work group runs on a specific compute unit. So let's say the minimum amount of work we do is the work item, okay? If you are, I don't know, running a vector addition of 100,000 elements, you will have 100,000 work item, okay? Organized by work group. Under the hood, what we have, and I will not tell you more about the execution model because otherwise we are lost and we don't see any code, right? So work items have the capability to work in a SIMT fashion, so single instruction, multiple thread. What does it mean? This means that, for instance, if we are on an NVIDIA hardware, by hardware definition, we have 32 work item, which can execute an extraction at the same time. Okay, on NVIDIA it's 32 and it's called VARP. Okay, an NVIDIA VARP, which in Kronos we call subgroup. Okay, if you have an AMD GPU, it's called, they call it wavefront, and it's made of 64 work items. But again, if you use Kronos terminology, this is just a subgroup, okay? So the subgroup is an abstract concept which is then mapped on an NVIDIA VARP, on an AMD wavefront, or on an Intel Xe vector engine, okay? Which on Intel GPU, is you can even change. There is a margin to change the size of the subgroup. while on the other architecture is fixed size, okay? So this is the execution mode. What does it mean this? We will see later. I have some code showing you the subgroup, but the idea is that you can have a very quick synchronization for between the thread in a subgroup, and you have the hardware provides primitive for operation within those subgroups. So you can do things very, very fast if you are within those 32 or 64 work items working together. Finally, and then I stop with architecture, we start to see some code. What is interesting about the GPU is the memory model, okay? So it is a relaxed memory model. Relaxed memory model in the C++ memory model exception is the weaker one, which is bad for coherence, but we don't need coherence or computation are all parallel. So it's very good for to have very quick memory access. So this is one of the key idea behind the GPU. We don't have all the silicon we have on the CPU for cache coherence. We just have a relaxed memory model, and we can provide very high computational power. Overall, the idea of the GPU memory model is that we have, of course, we have the host memory, the one on the CPU, then we have the device memory. On the device, on the GPU, we have a global memory, which can be accessed from any work item. We have a local memory, which is small but very, very fast, order of magnitude faster than the global memory, and is available for each workgroup. And this is key for performance. If you can use it, this will give tremendous speed up. And finally, we have private memory, which is local to the work item. Okay, so this was just a 15 minutes introduction to a GPU architecture, but let's see how to program it. So important notes. I assume most of you already had access to Leonardo, okay? If you do not, I will provide also an alternative setup. But the idea is that, every time we log into Leonardo, you need to do those few steps. You need to create a certificate and then log in into the machine. Then we will do SQL programming. SQL is a standard. There are many implementations. The one I'm using is one API. If you are trying this in your system, what you have to do is to install, and are the steps if you have an NVIDIA GPU, okay? Then you have to install one API. You need to install a plugin from CodePlay, which is a backend for NVIDIA. And then you typically one API, like any Intel compiler, you need to source a script, and then everything is working, okay? And you can download the examples. If you're working on Cineca, I just prepared a single script, which is this one. Is this one? Yeah, you need to just type source Leonardo pub. This is a public installation of one API. This is the work path. Just copy paste on your shell, and you will have the system working on your account. Okay, this is just an installation of one API already configured with the NVIDIA, so where you can see the NVIDIA GPU. Then you need to do a couple of module loads for Git for CUDA 12.3, and then you can get the source code from this GitHub repository. And on the GPU folder, you will find all the code I'm showing you today. So if you have access to the slides, the information on the slides, you can try now, you can try later. If you have no time now, or for some reason the cluster is particularly busy, you can try this alternative setup, okay? You just go to this web page, and for each code I'm showing, there is a link to Compiler Explorer, okay? Compiler Explorer, it's practically a web tool. It runs on the browser. The code practically on Compiler Explorer is running on an Amazon instance, so it will be CPU. But what is beautiful about SQL is that it works also on the CPU. And on the CPU subgroup, they become SIMD vectors, so IAVX instructions. So it is truly portable at the point that the same program also works on the CPU. The code, one small notice, the code on Compiler Explorer have very, very small size on purpose, because it works with a timer, you cannot really run the same code on the GPU and the CPU, especially if you run a very large program. Okay, so this is the setup you can try right now. Meanwhile, I do the lecture, you can try. Okay, and a final note about the, if you're looking for more information, I recommend this book, which is free. You can download it from the editor. This is a book from the Intel team, Intel One API team, and the book is freely available, and you find more or less all the topics I'm going to introduce you now. Okay, but so let's move to the code. So what is SQL? SQL is a single source, which means that both the host code for the CPU and the GPU and the device code for the GPU stay on the same code, which implies that the compiler splits the two and compiles the two as a two independent translational units. It's high level, and we will see this is relatively easy to write SQL code, few line of code. It's standard C++, so it's fully aligned with the C++ standard. In particular, SQL 2020 is aligned with C++ 17. And it is, thanks to, we will see later, thanks to very nice design for the infrastructure and the backend, it is really portable and can work on many GPUs. So CPU, GPU, FPGA, and other accelerators that are support for tensor processing unit and so forth. Okay. As of today, there are also tools that help you to do the porting, for instance, from CUDA to SQL. For small code base, they work quite well. There are many implementations of SQL. Well, we have, let's say, the standard one, which have been tested by many users, and they are under ratification, under CTS approval. So they will be officially recognized by Kronos as official working implementation. One is the one from One API, which actually it's open source code, and the same code base of One API is being used by other company, for instance Samsung, to test their PIM processor, for instance. Or One API is also being used by Huawei for Huawei Bisheng C++, which can target Ascend AI chipset. Okay, we have another open source implementation. It's called oh, here is written IPSQL. Actually, the correct name is Adaptive CPP right now, which is also very interesting. It's a very different way to map, for instance, the NVIDIA GPU. It's always good to test more than one compiler. Sometimes one is better than the other with some specific codes. And very important is that work in progress is the upstream of SQL to LVM, because this means that in a close future, any LVM installation will have a -f SQL flag supporting SQL. And there are many more, okay, many more. But it's very interesting that is now SQL going also on the embedded with Huawei and Samsung. So SQL has a platform model, more or less. I already told you about the platform model. We have host and device. On the device, we have a global memory. We have many computing units. What we do is to write some SQL code that push command to a queue. The queue is connected to a device. We can have actually more queue to the same device, but each queue can point to only one device. We submit our job to the queue, and then everything is asynchronous. Okay, this is typical asynchronous device. And what we do is very common with many parallel programming models. So practically, we translate traditional loop into parallel for. Okay, this is typical in most programming model. Parallel programming model do this. No, so the idea is that this is a SaxPy code. You see, it's just a for loop. And what we do is to take this for loop and make it a parallel for in SQL. Okay, this is the main idea. Now I will show you finally the first SQL code. That's it. This is the first SQL code. This is a SQL implementation of SuckPy. It's all on this. It's 20 line of code, okay? And a single source. So this is host code, and then when you see this parallel for here, the single line within the parallel for is device code. This is GPU, all the rest is CPU. The compiler automatically take off the GPU part and compiles it on a different compilation toolchain. This is standard C++. If you want to try this on Cineca, you need to use the ICPX compiler. After you run the script I provided you before, this will be available. Minus fsql always. Minus fsql target and ppd64 NVIDIA CUDA. This is specific to Marconi, to Leonardo. Okay, this you need it. Otherwise, you may have a runtime error. Okay, and then you can submit your job. For instance, you can do srun. You need to run on the booster partition, and in this case, we only ask for 1 GPU. Okay, you can also ask up to 4 GPU when you stay within one node. Okay, these two lines should work pretty easily on Leonardo. So what do we have here? So we have a typical C++. Are you familiar with C++? More or less, okay. Familiar at the point that you know what is a lambda function? Do you know what is a CTAD? CTAD maybe not. Okay, we'll see step by step. So we have in a single source, we start by using standard C++ vector, okay? Then, no, the first 3 lines are C++, right? Then here we use a queue. This is a SQL object named queue here, right? So what is this queue? It's a way to point to a device. In this case, we use the default constructor for queue, which the default policy is it points to the faster device in your system. So if you have configured everything correctly, it should point to the GPU. If you don't have a GPU, it will point to a CPU. Okay, it depends on your system. This default policy can be tuned. You can change it, and we will see this later. So this queue at the moment here, if we run this with this command on Leonardo, it points to the first GPU in the system. Then we create two buffer, one because we have actually X and Y vector, and we create two buffer mapping those two vectors. Buffer in SQL, like buffer in OpenCL, are a very, very high level concept. They are not yet bounded to any device. So you can use in different devices if you want. Okay, this is a very, very high level concept. And actually what I'm showing you now is the buffer accessor memory access model. There are two memory models in SQL. The other one is called USM. The other one is very, very low level and closer to CUDA, while the buffer accessor is really high level. And it's high level because, for instance, buffer are abstract and not bounded to any device. Then we have a range object. This is particularly the concept of range is particularly the concept of what is my iteration space. So if you have a for loop, actually the range is exactly the number of iterations, right? From 0 to size -1, and therefore it's a single dimension object with the sides. We can also have 2 and 3 dimensional range. Okay, now this is a very simple case with 1 dimensional range. Then we have we need to send this command to the GPU, and we do that by using the submit function on the queue. We submit, and okay, here may be confused. This one is a lambda. Okay, this is a tiny anonymous function. All of those lines here, you can even write in a separate part. Okay, we write this way because it's very, very efficient. In few line of code, you write a lot of stuff. What we do here in a submit is to declare one parallel for. We can only have one parallel for in a submit. So what we do practically is to have a command group handler with some command. those commands are practically parallel for command and accessor. What is an accessor? An accessor is an access definition. This is the moment when SQL knows that the specific kernel on this GPU will access to a very specific buffer. Okay, and for each access we can optionally, but it's very good to do it, specify, for instance, if we are accessing read-only or read-write. Those information are very important because those are provided to the runtime. SQL is a compiler, but it is also a runtime that keeps track of your data dependency. And if you write our program properly, the runtime is capable to beat data dependency graph with very high accuracy, which means higher performance, higher capability to hide latencies, for instance. And practically what we're saying here is that, look, I have X and Y buffer. I will use both. I will use the X buffer with the X variable and the Y buffer with the Y variable. And then later is my parallel for, where this is yet one more lambda, but this lambda here will run on the GPU. And we will have this executed for each processing element. So if the size in this code is 10,000, very tiny number, okay? As a side note, if you are working on a GPU, less than 100,000 thread, it doesn't even make any sense. Okay, 200,000. That's the number. You are not fully utilizing the compute unit. Okay, so this is a very tiny example I use also in Compiler Explorer just to explain. So back here, so practically we are running this parallel for 10,000 iteration, and then this is the body, and this is the SACSPY code. This is exactly the same code we saw before. Here we define the behavior for a single iteration. And you see here we are using X and Y, which are accessor, okay? Under the hood, accessor has a type and has the same type of the buffer. It's a template object, but you don't need to write the template here because on C++17 you have a nice feature called CTAD, which does type inference. This is under the hood. SQL uses a lot of this feature to make the code very much nicer. If you see previous version of SQL 121, this was more convenient to use auto here, but here you can just type accessor, okay? Even if you don't know all the C++ feature, doesn't matter, just type accessor. But what you have to know that Y has the same type of the buffer, which is float in this case, okay? Okay, so what is the parallelism? Is the parallel for? That's it. Parallel for is where the parallel is, okay? Now, when we do this computation, now remember everything is asynchronous. The problem is that we need to get back the results, and we need to get back the results when the computation is done, not early. So this can be done in many ways, okay? One of the way I think is the most efficient is by using the host accessor. By using the successor, I'm saying this is a synchronization on the Y buffer. So when all the computation on the Y buffer are done, please send me the data to this YRS successor. Implementation, how this is done, it's up to the compiler. Okay, it can be a new buffer, can reuse existing one, doesn't matter. But this is a synchronization. Then if you want to print your results, you need a synchronization indeed. Okay, if you don't have this line, what happens is that you send your computational kernel to the GPU. The GPU finish and start to send the data back. Maybe you have already printed. You need a synchronization, right? You always have this pattern: send the data, compute, and then going back. Okay, at least for symbol kernel. Okay. I mean, you can even try right now. No, this is a SACSPY code. You can try, if you go on the web page, you can try the link to the SACSPY kernel on Compiler Explorer, or you can run those two commands on Leonardo. Okay. Um, yeah, and as I said, the host accessor is a blocking call. Now I will show you SuckSpy again, but adding a little bit more feature. First of all, the queue creation. So there are many ways to create the queue. This is very interesting and rather flexible. You can use what is called a device selector. What if I want the CPU instead of the GPU? What if I have a embedded system with FPGA, embedded GPU, embedded CPU, and I need different ones? No, I can create more queues, and each queue will point to a different device. And you can do this by using a GPU selector. You see here, this time I have a GPU selector. It will pick the first GPU in the system. You can use a if you have multiple GPU, you can do something like that. Give me all the GPU, and then I pick the first one. This, if you're working on Leonardo, as is very interesting, you can create four queue in this way, no? So you can have four queue and submit different job to the different queue. Or you can also use what is called aspect selector. So please give me a device that supports 14.16. One, okay? The first one you have. Or in this case, we have choose aspect. I want a GPU, but it has to be a GPU that supports 14.16. And this can be interesting if you want to have an early error on feature not supported by the hardware, okay? Plus, there are, this is the standard, okay? But some implementation like one API, they also provide external environment variable to select the GPU for you with the default queue. No? If you want that the default queue by default picks the third GPU in the system, you can do it externally on the as a environment variable. Okay. This code here, so you see you have this GPU selector in SuckSpy device code, the one I shared with you in the GitHub. Actually, I commented many lines. You can test all of them on different way to pick your GPU. And in this case, you see there is a try catch. Now, I had a little bit more feature here. So first of all, there is no synchronization with host access like before. But the code is still working and you can try it. There is still a synchronization. The idea here is that is to exploit a very nice property of SQL objects. So SQL objects are RAI. What does it mean, RAI in C++ terminology? Resource acquisition is initialization. The idea is that I have an object with a given scope. When I leave the scope, then it automatically synchronize and deallocate by calling the destructor of the object. In this case, the buffer object, when leaves the scope, here, you see, here we have some buffer. We added those parentheses here. Those parentheses means that when I leave this statement, no, when I leave this block, there will be a buffer deallocation, which by standard, it implies a synchronization. So when I leave this block, all the buffer will be synchronized with the host. Okay, this is another way to implement synchronization. Here we are synchronizing both X and Y, so this is all successors are more precise, right? And this works pretty nicely. The only thing you need to pay attention is that buffer have a reference count because you can copy, and if you use many of them and you start to copy within them, synchronization may take longer. So in this case, the synchronization is within, you know, the is implicit. So there is an error in this slide. It's not explicit, it's implicit. or you can make it explicit also by using a wait. We will see this later. Exception handling. So there are two kinds of error in SQL. Very, very briefly, we have synchronous and asynchronous error, okay? Synchronous error are typical error. For instance, I cannot find a device, or the queue is not working, or things like that. Let's say error can be recognized easily on the host. Those kind of error can be catched with a try catch, okay? And here you have the error. Actually, they are synchronous, so you may even have the same API depending on the error, returning an error. Of course, if we have an error on the device, the error cannot be synchronous. Okay, so this problem can be solved by having a try catch surrounding everything. Typically, error are also thrown when we have a queue or a context destructor. And we also have a queue command is called wait and throw, which is a synchronization of the queue that particularly what it does is to wait until all the commands are gone and check if there are errors on the queue. Okay. Okay. So this was the first SQL code. Okay. Now I will incrementally add a little bit more feature. Okay. And to do that, I will show you a matrix multiplication. Okay. This is very, very simple code, but very, very cool because you can always add something to make it faster, right? So matrix multiplication, I assume all of you are familiar with this, but practically what we are doing is to have two matrices. In our case, they will be all squared. And to compute, for instance, the element of this value, we need one row here and one column here. So we need to work on two dimensions. So here we see a very simple matrix multiplication. So what we did here is to use again the buffer and accessor. Type is two-dimensional. Very, very cool is that buffer can be not buffer in SQL are typed. Okay, you see buffer. This is a buffer of float, and this two means it's two-dimensional. But two-dimensional is not only the data, but also the computation. Now, if we implement matrix multiplication, we have two parallel 4 and then one more for the k value. No, so what we do is to use as a range a two-dimensional range you see here, and the size this time is side times side. Okay, the very same code we saw before, we changed very little. So we are using two-dimensional data and two-dimensional parallel 4, and the rest is pretty much the same. We have a parallel 4, and we have accessor for the input and the output. Notice that we use read only for the A and B, and for C the output we use write only. Okay, and then we have our parallel 4 with two-dimensional range. Okay, at the end we use an host accessor on the outputs to synchronize and print the results. Okay, that's it. This is a matrix multiplication in SQL. Now I have a question for you. I told you that there is data movement implied, no? Because we need to move the data from the CPU to the GPU, going back, right? Where is the data movement? It's in the buffer, but because of the accessor, okay, this is a first point. The buffer accessor mode does not explicitly define the data movement. It only defines the dependencies, right? So practically, when we enter the parallel 4, the SQL runtime knows exactly what data is needed, and this is a lazy policy. The data movement will happen at that time. Then the buffer, which when we create it is abstract to the hardware, no, it's abstract to the device. And at that specific moment, the runtime knows where this buffer is needed, and the movement between CPU to GPU will happen. Then when we leave here, the successor will do the other way around. Okay, data movement is implicit, and data movement, if you write very, very large application, this is a very typical source of error. This is because you're using array semantic. Okay, if you do some C++ programming, you will know this is a well-known technique to reduce error. Okay, um, so why this is possible? This is possible because when we use accessor, the SQL runtime is capable to draw a graph of data dependencies. Okay, I will show you a little bit more complex code, but it's not so complex. But in the end, we have just, in this case, we have parallel for there, parallel for there. We have 4 parallel for, right? If you follow the data dependencies of this code, you will see that some data is written in the first parallel for instance, A, and then is read in this parallel for here, the third one, right? So those information are provided to the runtime by the use of accessor. Of course, accessor must be properly written, right? With read and write written the right way. And implicitly, there will be this data dependency built by the runtime, okay? Then the SQL implementation is free to do whatever it likes. Typically, it is executed in the order of submission, but the specification do not set, if you have a capability to overlap computation, the runtime is free to do it. No, GPU can do also concurrent execution of kernel, modern GPU, okay? Because we have different streaming multiprocessor on NVIDIA. One parallel 4 can run on one, another parallel 4 can run on another one, and the problem is the knowledge of the dependency. So the knowledge of the dependency is known to the runtime system, to the runtime of SQL because of this, okay? And this, because we're using buffer accessor, this is built automatically. This is because kernel are by default out of order. And this is different from a standard CUDA program. Standard CUDA program are in order. Okay, this is a very strong difference. However, we can also use in order queue, and to mimic, let's say, the same behavior we will have in CUDA, by using, when we create the queue, we can use this property. It's called in order queue. When we specify in order queue, we are practically telling to the runtime, forget about the data dependency, just use as a ordering the order of submission. And this means that the graph I previously shown becomes this one. Okay. Okay, so and this is the default behavior most programming model. No, CUDA, HIP, they use this programming this approach by default. Then, if you want to use out of order, you need to add use additional library like CUDA graphs. I told you we are using buffer accessor, which is the high-level approach to program SQL. There is one more way to access the data, and is unified shared memory. Unified shared memory, it's closer to CUDA, to low-level programming model. It's a little bit less flexible, but actually it's more powerful if you want to integrate pre-existing code base, because it's a pointer-based access to the data. When you use accessor, use the accessor. You don't use a pointer, use accessor, right? With USM, instead, we use a lower level programming model. So this means that we use a malloc and a free to allocate the memory. But malloc and free is different than buffer, because malloc and free need to specify on which queue, on which device I want to allocate the data. So buffer is abstract. Okay, when we use malloc and free, then we are very, very specific. There are more way to use USM. I will just show you implicit USM, explicit USM. Particularly implicitly USM, what happens is that we use malloc shared. Okay, this is still higher level. Okay, because as you can see, we have malloc allocation where we specify this malloc is different from the normal malloc, because this malloc takes as an input also the queue. So this is a malloc which is creating data on the GPU. right now. It's not lazy. Okay. Then we initialize the data. Then we have a parallel for instance. And then we have to use, oh, very important, when we use USM, the runtime doesn't know about data dependency. You need to synchronize the code. The runtime will not do it. How do you do it? By using the wait, okay, on the queue, the same queue we use it here. And then when we have done to do all our computation, we must use the free. This is not the free you have, this is a SQL free. It takes as a second parameter the queue, okay? This is a little bit lower level because we need to use malloc and free. But still, because we use the malloc shared, still data movement is automatic. There is one more way to use it, and it's by using a malloc device. Okay, this is even more, when you say shared, it means it implies it's shared between CPU and GPU, not between host and the device you specified. But there is another way to use malloc, and is this one. And you see the code is start to getting very, very verbose, and it starts to look like CUDA, right? This is very similar to CUDA. Why? Because we need a malloc device, then we need an explicit data movement, which is this memcopy, where we specify the buffer here, which has to be a buffer previously allocated with a malloc device, then the data here, and you need to write a memcopy between CPU to GPU, one for each buffer. So this memcopy is actually moving the data from the CPU to the GPU. Now, we didn't have this problem with using the buffer accessor model. Here you have to do everything by yourself. Moreover, you need to synchronize it. There is a wait here, there is a wait here. You need to synchronize everything, right? You cannot start the computation if you didn't complete the movement, right? You cannot start to print your result on the host if the data, the results, didn't come back, right? So this is the lowest level approach to programming SQL. This is actually very, very fine-grained, low level. It's the closer to CUDA. Probably if you're doing a porting, this is much better than buffer accessor. But if you're writing a large application from scratch, buffer accessor is much easier. It takes for you really much less time. Okay, so this is the idea of SQL, is to provide two different approach to GPU program. Okay, and let's say we have seen now what was the fundamental, no? Now we will have a look to a little bit more advanced features. And for more advanced features, I mean features that need a deep knowledge of the architecture. And in particular, we need to know, now we need to exploit the memory model and the execution mode, right? So as I told you, computation is not flat, right? It's not just a parallel for work items are not all the same, no? Work items are organized in work group, and then they're organized in smaller subgroup. Okay, there are two hierarchy of group, right? So we have our work group, and now what we do now is to move from range to ND range. I show you a parallel for using as a size parameter a range. Now, range means any number, okay, even a given number. No. Problem is when we want to go, to write something that is closer to the hardware, we need to use size that matches our architecture. So the idea is that, first of all, we need to define a work group. And the work group, it cannot be any size, no? If you are running on the Ampere, on Cineca, you are doing some tweaking, you will define what is called a local work group size, which is the size of one ND range, which typically, depending on the program, can be 256, can be larger, or can be even smaller depending on many factors, okay? And it has to be a multiple of 32 on NVIDIA. Why? Because if I told you that work item works by 32, then we don't want to have sparse computation, right? So things gets a little bit more complicated. So SQL has many parallel for. Let's say it has two different parallel for. One takes any input size, and this is the range object. One instead, it's the high performance version, and it takes as an input an ND range. The ND range has the global size and the local size. So we need to specify how many threads I want running on a compute unit. And this is on GPUs, this is a very sensitive parameter. This is sensitive to performance. If you do GPU programming, you need to tune it. For many reasons, no, like you have graph algorithms, for instance, very likely you have you have a lot of thread divergence. Smaller one may be better, or maybe register pressure and pressure on local memory is different. Then you still need a different tuning. This is something you need to be very, very careful. So typically, we define the size of the work group, the size of the subgroup for NVIDIA AMD is fixed. You cannot change it, right? It's 32 for NVIDIA, 64 for AMD. On Intel GPU, typically you can pick between two free sizes. This is because Intel GPU have a Intel GPU SIMD vector are mapped on SIMD-like architecture, which is very, very flexible. And so the idea is that on this advanced part, we will see how to use the workgroup, subgroup, group algorithm, and so forth. And I will cover all of this except for specialization constant. Let's say I will cover the major points for performance here. So as I told you, we have work item and we have workgroup. And repeating a little bit of stuff here. And then we have subgroup, which are mapped on VARP on NVIDIA, Wavefront on AMD. On Intel, they are called XV. And if you're running on the CPU, like if you're running on Compiler Explorer, subgroup will be mapped on a AVX vector, x86, no? On Intel. So why are subgroups so important? Because if we know subgroup have many operation called, let's call it a collective operation, you can find different name on different vendor, which can be executed very fast. So first of all, you can have a very fast synchronization between threads belonging to the same subgroup. And then we have a number of operations, and here is a list of operations which can be run very fast. We have a broadcast, which means all the threads reaching the subgroup function. So here you have to be careful. So when you use subgroup, there should not be divergence. So all the threads in the same subgroup, so in the same VARP, so let's say every 32 thread, they need to reach the same instruction. At that time, the subgroup function behaves with a collective behavior. What does it mean? For instance, if I'm using a broadcast, then one value of the subgroup will be propagated to hold the work item in the subgroup. This means that all the threads will have the same value. Or broadcast is an example. We have the voting primitive, like any of, all of, you have to think this with like bit mask operation within a subgroup. We have shift and permutation. You can move the data around between subgroup. Yeah, this is very powerful because this means this is a way to communicate between different threads, different work items, and it's very fast. So the idea is that if you can do to a very narrow scope within the subgroup, you can do this very fast also on the GPU. And because GPU has a weak memory model, we really need this kind of synchronization. And we have many, many more. We have the reduce, join exclusive scan, and so forth. Very important, we also have a group barrier, which is a barrier limited to the group subgroup. Actually, the way specifications are written, you have those operations both for subgroup and workgroup. Okay, but you need to be careful because it's big difference, no? If you do subgroup, you're synchronizing between 32 threads. If you do workgroup, you are synchronizing between 512 threads, maybe, no? And the problem is that by the hardware provide very fast synchronization only for the subgroup side. So you need to be very, very careful when you use this operation. This is now a matrix multiplication. You have this code in the both in the GitHub and Compiler Explorer if you want to try it. Rewritten with a group broadcast. Okay, the idea is that this SG is a subgroup. The idea is that when I get there, where did I define it? Here it is. Okay, this is a subgroup object. Auto can be used to replace the type. My bad, I use auto here. Subgroup, I can get the current subgroup, and from the subgroup I can call the broadcast, which takes a tile and the key element I want to broadcast to all the work items within the subgroup. Okay, this particularly helps, matrix multiplication. No? On one dimension, you can take one element and spread over all the elements in the workgroup. This make on the subgroup. This makes it faster. Okay, because this one is mapped on the hardware, very fast hardware. So this is an example of when you can use subgroup function to make your code faster. Still matrix multiplication, but slightly faster. Okay. You can also have reduction within the subgroup. In SQL, do you know what is a reduction? A reduction operation, I mean, suppose you have an array, I want the summation of all the elements of the array, or I want the max or the minimum. So any operator which has commutative and associative property can be used for a reduction operator. In SQL, the reduction is part of the language, and there is what is called a kernel reduction, which is a different parallel for, which takes a reducer as a parameter. And the idea is that reduction is supported by the compiler. This is also very cool. If you have written CUDA code, by the way, who knows CUDA here? A lot of people. How many reduction have you written? If you did real CUDA programming, you write a lot, right? And unfortunately, some CUDA version they get, you need to tune it, right? So if you use famous Harris reduction algorithm, which is now 10 years old or longer, it doesn't work with recent GPU because of independent thread scheduling. So this is a kind of code that you cannot make easily portable. Again, if you look at this very, very now old reduction code, you will see that it makes the assumption that the war pass 32 threads, so it's not portable. On AMD, it doesn't work, right? On SQL, the idea is okay. Let's make SQL. Let's make the reduction part of the SQL standard, so that it's up to the compiler to optimize it, not to the user. Okay, this is a very, very high level feature. So this is the way you do it. So in this case, we want a reduction. This is a dot product. Dot product. You have x, you have y. You do a multiplication, and after multiplication, you sum up all the elements. Okay, the sum up is a reduction. So what we do here is to have multiplication in the kernel. This is the parallel for, and after the multiplication, we have a combine operation. How is this possible? It is possible because we defined a sum reduction. This is a reduction object here. using plus as operator. If we wanted to have the maximum, there is a max operator and so forth, okay? And then in the parallel for takes an extra argument, which is a reducer object, okay? So these two tiny chains allow you to do a reduction, okay? And this is performance portable, right? Because you can have this optimized by the compiler on your specific target hardware. It works on AMD, it works on Intel, it works on NVIDIA. Okay, this is a very, very interesting feature if you care about performance portability, and it's 3 line of code, no? CUDA reduction is typically in CUDA typically is 50 to 60 line of code, depending on the optimization you are doing. Plus, you necessarily need some code to, that adapt your code path to your architecture, because the reduction you write for an ampere is different from the one you target an old generation. Okay. Okay, so next, one more advanced topic is the use of local memory. Okay, as I told you, we have global memory, can be accessed by any work item, but within the compute unit, we have what we call local memory. CUDA, in CUDA terminology, is shared memory. Okay, Kronos terminology is local memory, which is very, very fast. Very, very fast, okay, but tiny. If we can make our argument to use this local memory instead of to have access to the global memory, we can have tremendous speed up. And we are talking about even 10 times faster, depending on the code. So this is very, very, very important to do it. I'm showing you here now a matrix multiplication with tiling, which use this optimization. Matrix multiplication, this is the symbol code, okay? When, I don't know if you're familiar with tiling, but the idea is quite simple. Standard approach, the one I just showed you the code, you compute the output here, you load this data, you load this data, you do this single wise, no? Each element wise, right? But when you do by tiling, you move, you compute the output for a whole tile. Ideally, the tile is mapped into a work group. So you are running, for instance, 256 threads all together, computing the output for a tile. And this idea is cool because we can use the local memory to load a piece of A, a tile of A, a tile of B, compute our output, and write down. Then we accumulate the results on C, no? Then we take another piece of A, another piece of B. Those small pieces are tile, right? So we work tile-wise. So the idea is that our iteration space is not the usual one, but it will be tile-wise, okay? Overall, our program will look like this, okay? We have the same as before. What we have to do is to declare the use of local memory. We do this by using this local accessor, which is still, in this case, is integer, two-dimensional. We will call it tile, okay? Tile A and tile B. Then the rest is pretty much the same. Our parallel for will be different. And here is the parallel for. You see, when you do tiling, you typically, you add one more for loop to your code, because you need to iterate for each tile. So this code in the end is very similar to the previous one. The difference is that we are not accessing to the global memory, but we are accessing to tile. You see, here we prefetch the data, and here we use tile for the summation. What you have to be careful is that when you prefetch the data, you need a synchronization. You need to be sure all the threads have done the prefetch. Otherwise, you may have race condition. Then you do the computation and you had another synchronization. The synchronization you need here is a synchronization by workgroup, and it can be done in this way, group barrier. group barrier, in this case, it takes a work group, okay? So practically, we had it, local memory and two synchronization, and this code is 8, 10 times faster than the previous one, because by working by tile, we're using a very, very fast memory, and we don't have to access the global memory all the time. Is that clear? This is a little bit more advanced, okay? I got for granted that you know a little bit about tiling optimization, but overall, any program that has multiple access to the global memory, and very important, those access are shared between different work items, then instead of having different work items accessing to the same data, the idea is very simple. Move this data from global to local memory, and then all the access will be much faster. Now, the problem is that the local memory is not very big. So I think here, I don't remember what we used in the code, but still cannot be very large. Okay, it's limited. But still, this is enough to save a lot of time, latency time to access the memory. Okay, this is a very, very GPU architecture are very, very sensitive to this kind of optimization. Using the local memory is probably one of the most effective optimization you can do. When you start to do some optimization, first things you have to think, how can I use the local memory? Okay. About memory, so I told you that GPU have a relaxed memory model, but SQL use the same memory model of C++. Now, C++ has a definition of memory model. We have relaxed, acquire, release, acquire, release, and sequential consistency. Okay. By default, your code in your parallel 4 has a relaxed memory model, which is the one matching the GPU. However, if you want, you can add an atomics. Okay, and there is a support for the atomics. When you write an atomic, you need to define what memory model you're ordering you are using, the scope, if your atomic is within the subgroup or within the workgroup or for the whole device, for instance, and the address space, if you're working on local memory, private memory, or local memory, okay? This is a very tiny, this is just a counter, just to show you how to use this feature. Recommendation is to do not use it because atomic on the GPU are terrible, any architecture. So GPU are not very good in this, but sometimes you need it, okay? So try to limit your atomic in your code. And in case you need it, the syntax is very similar to C++. This is good and bad because actually else in C++ is very verbose to use an atomic. You need to do all of this. You need to have an atomic reference with the type, the memory ordering, the scope, and the address space. Okay, it's a little bit verbose to write an atomic. I recognize that. It was a choose from the working group to have the syntax the same of C++ with really minor changes. On the other hand, it's good that expensive things get noticed, right? Atomics are very expensive computational wise. So I more or less finished with the foundation and advanced part of SQL. Now, in last half an hour, I don't know if you have some question now. Maybe now there is some time for question about the topic we did so far. Otherwise, I move to the next part, which I practically will show you some more advanced topic. This part is called Beyond SQL because what you see here is not yet in the standard, are features that are or either proprietary or research project. Okay, so last 30 minutes I will show you something more research oriented, but in my opinion, very important because it's where the future of SQL is going. Okay, so first of all, SQL is a standard, but what is very important is not the standard, but it's the implementation. And practically all major implementation of SQL are open source. In particular, one API is now joining the Linux Foundation, and there is now a new foundation under the Linux Foundation umbrella. It's called UXL, which is managing not only is using SQL as a compute layer, but actually as a collection of library, all open source. Okay, the idea is that when you do GPU programming, heterogeneous programming, you just don't need an open standard. You need an open ecosystem. Okay, this is very, very important. And this practically, if you're working with one API, you have all this library. You have the math kernel library. This is very popular library for math operation, neural network library, collective communication library, and so forth. The idea that all this library can communicate each other. Okay, so and everything is open. So between them we have, for instance, one DNN, which is a neural network library. I mean, as you know, AI now is everywhere. Indeed, both the ecosystem and the standard are caring about that. And one way to support this is the SQL join matrix extension. Now, one note: this is not standard yet. This is right now, it's only on one API. You don't find it in other implementation. But the idea is quite simple. The idea is that to have a unique interface to support all this tensor, let's call it tensor operation, okay, provided by the hardware. What is the hardware for? What is the hardware doing for AI? The very, very end, okay? In the very, very end, AI is about this tensor processing unit. It's about two features, right? One is to have what is called mixed precision, no? So to have floating point with a shorter number of bits, not like floating point 16. By the way, floating point 16, there are different standards. There are BF16 and F16. They are different, okay? Now there are also 8-bit coming, and there are also integer fixed point notation, okay? So one is this is one aspect of AI. The other one is the capability to perform matrix multiplication, or more matrix multiplication, through in a fast way. So if you are modern CPU, no, the new CPU from Intel, they have IMX instruction, okay, which is more or less, you have a vector, you have your small matrix element in your vector, and then you have a operation within this vector, which actually calculate a very small matrix multiplication very fast, and it's very fast because it's within the vector, okay. On NVIDIA, we have what is called the tensor core, which is the same concept. On Intel, we have a similar concept, which is called the XMX instruction. So as you see, all the hardware are more or less doing the same things. They are providing support for, let's say, half precision and fast matrix multiplication. So the idea here is to support practically an API, which I have to say is not really high level, in my opinion, but it's because it has been designed in a way that is very, very similar to CUDA tensor processing API, okay, which is also very verbose, okay. But the idea is that we have a type which is called join matrix, which works like a subgroup function, okay. So all the threads in a subgroup operate to calculate a small matrix multiplication. In fact, when you use this feature, see on the top, you need to use bfloat16. bfloat16 2 is a small, is a two-dimensional matrix of bfloat16. What is a bfloat16? It's a floating point using 16 bits. Okay, this is the one we typically use in AI. And so the idea is that by having this extension, we need to have this data type called join matrix. We have an API to fill this data type. You see, the first argument is a subgroup. So it has been implemented using the existing subgroup abstraction. The same way you have subgroup calculating broadcasts or doing synchronization, you can also use it to calculate a matrix multiplication. Actually, the operation itself is a math, so it's accumulated multiplication and addition. Okay, operation are true, no? And practically you have the API to fill, to load the data, to perform the math operation, and then to store. Okay. This one matrix apply. This works like a scalar operation. Is not real subgroup operation. So practically the idea is that if I use this API, then this will be mapped on NVIDIA Tensor Unit. On CPU will be used the IMX vector instruction, and on the Intel GPU will use XMX instruction. Okay, this is one idea to support AI on SQL. Okay, and this is currently used by 1DNN. One more very cool feature of SQL, this is also not standard, is SQL graph. And this is an idea that if you write tiny kernel, you don't care. But if you have a very large application, or think about real-time application, what do we do when you do real-time application? You typically have a pattern in your command. No, you repeat the same command again and again. I want to run kernel 1, 2, and 3 for each frame for thousands of time. Okay, this is very common, but this behavior typically has an overhead on the runtime. Okay, and the idea here is to try to optimize pattern where the runtime can recognize those patterns. The idea of SQL graph is that practically you have two API. One is to record and replay commands. So think about this. I record it. I start my recorder. I do 3, 4 operation, move the data, compute this, compute that, go back. Okay. Then I stop the recording. Then I keep this as a single element. And then instead of submitting everything again and again and again, which is an increase in the overhead of the runtime, I have a replay command. Okay, this is one way to optimize the runtime overhead of our GPU operation, which is, you start to optimize GPU code. At some point, you will see that it will be very challenging to keep the GPU always busy. You start to feel the overhead of the host organizing the computation. So this kind of API are very important. At least we use it in some project recently. It's very powerful. And the API has on one end the capability to record. You have something like graph begin recording, graph end recording, and you can make and you also make explicit creation. Okay. One more very interesting feature. Even this is not very high performance computing. This is more embedded system. Is anyone here familiar with embedded system, real-time programming? So this is very unique to SQL, okay? And is a new working group within Kronos, on where the SQL standard is going to be improved. What improved means with compare many things. We can be like compare warning, new feature, and so forth, to make it safety critical. No, safety critical. No, when you write code for avionics, automotive, there are some very strong requirements in terms of robustness. And the idea is that there is a working group working on this. And practically, the idea is that, for instance, right now, focus points are to focus on offline compilation rather than online. Offline is much better for embedded system. To avoid dynamic allocation, to have deterministic error management, but to tell you one more, the buffer behavior. No, the buffer behavior implies that data movement can happen anytime, and this is not nice. No, you want predictable things. No, and there will be extension to improve this. So this is a very interesting direction. It's very early right now, still work in progress, but very interesting for the future, and there are industries spending money on this. Okay. So Now, last 15 minutes, I want to talk about some research projects we are running on SQL, okay? And here the idea is about how to extend SQL. And this is for me a very interesting feature of SQL. Not only is a very high level programming model, but it's very simple to extend it. And to extend it, I mean to provide to the language additional feature for which we wrote it, so the working group didn't think about it, okay? Other programming models are very hard to extend. If you want to extend CUDA or even level 0, they're not really easy to extend. SQL, being C++, being having all these nice features, um, allows to be easily extended. We designed two extensions to SQL. The first one is called Celerity. This has been designed with the University of Innsbruck in collaboration with the University of Innsbruck. The second one is called Synergy. This has been designed at the University of Salerno, so some of the authors are here. And this one has been published at Supercomputing last year, okay? Those are two examples of how we can extend SQL semantic to provide additional features. So the first one is called Celerity, and all of these projects are open source. You can go on GitHub and download and try it, okay? Celerity in particular has been also tested on Leonardo. And the idea is that we can extend SQL semantics so that instead of running my kernel on a single GPU, I will run my kernel on all the GPU in a cluster. For instance, I go Leonardo and I do my run with 64 GPUs, okay? What should I do to make my code working on 64 GPUs? So typically, what do? You use another library like MPI, right? You move the data between all the nodes with MPI collective. Then you run on each worker your SQL code, and then you gather, right? This is a typical pattern. It takes no very verbose. It's not really high level, right? The idea is that we extend the language with minor changes, and then we had under the hood a distributed runtime system, which that takes care of the data movement, data partitioning, and all the rest. So this is the API, okay? The API of Celerity for a SuckSpy kernel. So this is the SuckSpy normal one you will write in SQL, the one we saw before. This is the one we write on Celerity. You see the addition, actually all the objects here are using the Celerity namespace. So what you see, the distributed queue here is actually a new queue, a Celerity queue, which instead of giving you one GPU, it gives you a virtual GPU representing all the GPU of the system. So it's an abstraction. Then we have submit, like you submit a normal kernel, parallel for. The only other change we have is that our accessor in Celerity, they need one more parameter, which is called a range mapper. This parameter is a description of how the accessor is accessing the buffer. And practically, this is what is needed to the runtime to understand how to move the data between GPUs, right? So this is the only addition we have. So in this case, one-to-one means that practically we are accessing, with the iteration high, we're accessing X only for Y and Y only for I, okay? This means that there is a one-to-one mapping between the iteration space and the data space, okay? There are more range mapper. This is the key semantic to understand to programming in Celerity. All the rest is the same, okay? One note is that we only support buffer accessor mode because USM cannot be implemented so easily. Those are some predefined range mapper, but a range mapper is a lambda function. You can define your own. Okay, this is very flexible. And so this is practically one-to-one means that the single element is mapped to a single element. The work group is mapped to another work group. Okay. This is called neighborhood range mapper. Neighborhood, you can think about a stencil computation, or think about image processing. You're writing 1 pixel, you typically need to read from another buffer in a given neighborhood. Okay, neighborhood means that some extra data movement happens. No, you may get some data that belongs to another worker. So on the API, we have what is called a neighborhood range mapper, and it can be 1 or 2 dimensional. In this case, it's 2 dimensional. Then we have slice range mapper is the one we use in matrix multiplication, for instance. So what do we do? For this element, we need this row and this column, right? This is, in this case, we have a specific range mapper is called slice, but this you can implement your own. And this is all what you need to tell to Celerity to perform the right data movement. Under the hood, what we have is something like that. Practically, from the source code, we generate a task graph, and task graph is very similar to the SQL task graph, but then there is a command graph. What is the difference between those two data representations? That in command graph, we also, in task graph is closer to the code. Command graph, it adds the partitioning and when needed, the MPI commands, the data movement between nodes, okay? Here is where is the complexity, the command graph, okay? So practically, you have something like this. You have multiple nodes. Each node builds the task graph. The command graph is different on each node because different nodes they need to perform different communication. But in the end, each job will be mapped on each GPU, and the iteration space is split, right? If you have two GPUs, half of the iteration space goes to the first one, the other half to the next one. Okay, this is the idea. And practically here is how it works in real time. Let's say that. So you have the program code. Every time you have a submit, you have a task. For each parallel core, you have a task. From the task, then you generate the command graph. The command graph has kernel execution, but also has send and receive. Okay, MPI send and receive. Just to be clear. Okay, this is what a runtime system does. Okay, this is an interesting way to extend a SQL. Here reference paper. And we have been tested this in here. You see results for Marconi, but we run it also in Leonardo. There's a very, very good scalability. And if you want more information, you can find more information on the paper on the GitHub. Okay. One more extension I want to introduce you is one we developed recently in Salerno, and it's called Synergy. And here the idea is to implement a very high-level approach to implement energy efficient computing. Energy efficient computing, what I mean here in this context is to use frequency scaling capability from the GPU to reduce the energy consumption of a kernel. So if I don't know if you're familiar with frequency scaling, maybe you're familiar with overclocking GPU. That's in gaming community is very popular. But the idea is that you can change the frequency of which you run a kernel. What we did particularly in this work is a little bit more complicated than Celerity because we had to change also the compiler here, but it's still a very simple on the API perspective, high level, easy to use extension. And so what we did is to provide an API to introduce energy semantic. Then we have a compiler which uses machine learning. I will not tell you more about this, and if you're curious, I just drop you the paper. And then when you run this on a cluster like Cineca, Aslan plugin enable the energy capabilities. So this is the main idea. I just want to show you the API because it's a very good feedback for you to understand how to extend SQL. No, can be done in different way, but overall it's not very complicated. No? In this case, the API, we have API for three main features. We have API for energy profiling. What does it mean? I want to know one kernel, how much energy has consumed. This is the idea. And in Synergy, practically, the idea is that we replace the SQL queue with a Synergy queue, which is an energy instrumented queue. Okay, this is the only change we did to the SQL standard. Only one change, the queue. And when you submit a kernel, you can have this from the queue, you can call energy consumption or the kernel energy consumption or device energy consumption. We can do this both for each parallel 4 or for the whole device. Okay, this is a very easy way we extend the API to support energy. And this I want to tell you, this part of this is just API extension. No? This is just C++ code for this part of the extension. So you don't need to deal with the compiler to implement this. Then we also have capability to do frequency scaling, okay? And the idea is that for each, you can define, you see two numbers. The first one is the core frequency. The second one is the memory frequency, which unfortunately is not available on all the GPUs as of today. But the idea is that I can provide really the frequency to run a single kernel or to all the kernels submitted to a given device, to a given queue. Okay, there are two ways to work. You can work coarse-grained or fine-grained. And what you can do is to say, okay, this kernel, please run with this frequency. You see, this is a parallel 4 with extra parameters we provided. This is, again, library extension. This is just a simple library that provides this feature. Finally, and this part requires compiler support. Okay, this is not so simple as it may seem, but the idea is that rather than using just a number for the core frequency, we provide what is called an energy target. In this case, the energy target is minimize the energy delay product, which is an energy metric. Just to understand what I'm talking about, so if you take this, I think is a Black-Scholes code running on an NVIDIA GPU. So by default, if you do nothing about energy, you will have this performance, okay, normalized. But if you start to play with the core frequency, you may have all this configuration. You may have this configuration here where you say 20% of energy, you lose 20% of performance, but you gain roughly 10% of energy. And all of this configuration, you do not have access if you don't do this. So by default, you only have one, okay? The API we designed is to access all of them. Now, the problem is there are so many. It's very confusing for a user, right? So we provided some extension, no? So practically, if you want the one which minimize the energy, you want this one. If you want the one which maximize the performance, you want this one, right? Those mean energy and max performance are energy targets you can provide to a parallel 4. Plus, we support EDP and EDD2P. Those are well-known metrics if you are from the computer architecture. The problem of EDP means energy delay product. It's typically very close to energy, mean energy, and EDD2P is typically very close to max performance. So what we did is also to add more metric if you want a trade-off solution. So for instance, if you want a solution that allows you to save 25% of the potential saving you have, you get this point here. ES50 is this point here, ES75 is this point here. So you can really dig into all the Pareto optimal solution. It's a multi-objective problem. Or you can define the metric in terms of performance loss, okay? This is practically the idea of the API. Under the hood, this is because there is a machine learning model, not neural network, simple machine learning, but indeed very accurate. And we also have a Swan plugin, which allow us to run this on Cinega. Those results are from Marconi 100, so we don't yet have results on Leonardo for the energy part. But the idea we run this on two large applications, one is Cloverleaf and Miniweda. We could save 20% of energy on one end, and on the other application, 30% of energy. So this is practically another way to extend SQL. We only from the API, we only extend the queue in this case, okay? And last slides, this is another extension work in progress for approximate computing. This we're extending buffer and accessor in this case. So the idea that you can literally take all the semantic, can be the queue, can be the buffer, can be the accessor, and change it so that you can add an additional feature to your programming model. This is very, very interesting. And it's a feature no other programming model has, not in the way SQL does it. And this is really my last slide, so I even finished here. Okay. So for today. So, but I still have time for questions if you have any. So we saw more or less how modern GPU work, and we saw the main concept behind SQL. So the buffer accessor mode, unified shared memory, and the out of order default behavior, the in order queue, and so forth. We also have seen how in SQL you have this high level abstraction, but you can also program at workgroup, subgroup level, use group algorithms to implement synchronization. And this is mapped, this is portable, this is mapped, for instance, if you work on NVIDIA, on Cineca, subgroup are mapped on VARC. So there is a very efficient implementation under the hood. And we also seen some more advanced topic, in particular how the SQL ecosystem is not only the key concept of the parallel for parallelism, but we have extension for AI, we have extension for SQL graph, and so forth. Okay, and finally, I show you some research work that also provide you some insight how to extend it. That's very something unique to SQL. So with this, I conclude my lecture. So thank you very much for your time, and please, if you have any question, I'm here.
Any questions for our speaker?
First of all, thank you for the lecture. How an extension become parts of the standard in terms of time? How much time needed to become standard, and who is that make it? Thank you.
Okay, so this is a very good question. So first of all, an extension doesn't necessarily need to be in the standard, right? In the sense that in the moment it's on the standard, it means that all the vendor must implement it to be, unless it's an optional feature. Okay, let's say right now SQL moved very, very fast, but now it's moving through a more traditional approval ratification process. So you have to be member of the working group. To be honest, the working group is very open. So if you go on the SQL GitHub, you can submit your if you have some problem. This is also where for bug, and I can tell you those are really discussed in the work. Really, we discuss it for hours. Tiny feature, because tiny sometimes bug it hides larger problem. No, in terms of feature, the problem is this is industry. No, the good point is that it's an industry consortium. So of course the process is slow for ratification as an official standard. But you can have your own in extension. The problem is if your extension is a library extension, you don't really need a ratification for nothing. It will just work, like celerity. If it is a compile extension, it's more complicated. On the other hand, the good point is all existing implementation based on LVM. So it's not really hard to make your extension working on existing code. But the ratification process is slow because this needs time to, and I can tell you what I learned from staying there, no, in the work group. You can never guess the impact a feature can have on maybe other feature, no? Like USM has many corner case where you work on USM and then you want to go back to buffer. This is very, very tricky. It's very hard to predict all the side impact. That's why it's low. It's also because of maturity. When the standard is more mature, you need to understand better the feature. Even tiny feature, you never know. So this is my answer. So a little bit negative answer in the sense that it takes time. Okay. On the other hand, this is also because now it's a more mature standard, and all the vendor needs to understand. Also, I have to say, SQL doesn't like, the SQL working group doesn't like features that only work from one specific hardware. Okay, the idea is try to keep the standard portable between GPUs and possibly most accelerated. Okay, this is very important. It depends a lot on the feature, no? Hope I answered it. Okay.
Thank you so much for this lecture. It's very nice. I have a question about programming with the cycle. Uh, just to know, we can build also complex C++ programs, I don't know, with the class objects, constructors, and also using cycle to submit jobs to, I don't know, GPUs, accelerators, uh, parts of code, complex codes.
Yes, as soon as you do not use in the kernel function, so in your lambda, no, that will go on the GPU, you have to be careful this goes on the GPU. So this is very, very explicit in SQL, no? It's not like another programming model. You add a pragma, yeah, but this is going on the GPU is different, right? So you cannot use, for instance, virtual function on the kernel code. This is a very, so in my opinion, if you're doing high performance computing, you shouldn't do anyway, because it's known to be slow. But let's say it's oriented through modern C++, which is more using template rather than, virtual function, anything like that, okay? More or less, you should be able to do it. I mean, many part of the standard, you can customize it. You can customize a reduction object, for instance. You should be able to do. Of course, some features will not. The problem is there are features that do not work on the accelerator. This you must be very, very on the host. You can do whatever you like because the host will be compiled like normal C++ code. But on the device, you need to be careful.
Also another question regarding the creation of the buffers and actually no, the shared memory with the malloc free. There's no other way to do that, like with the new delete, like in C++, for instance.
Well, the USM, Unified Shared Memory, has malloc device, malloc shared, and malloc host. So there are many ways to do it. It's lower level because it binds your data to a specific device. So any subprogramming model very similar to CUDA, to heap, to level 0. So yeah, this is I mean, the other way is buffer access, okay? The standard provides you two memory access mode. This is the idea. One is high level, the other one is low level. And in some cases, you may need a low level one because maybe, it depends on your application, right? Yeah, I mean, this is the way. It depends what you're looking to. I mean, if you need to quickly run something on the GPU, you have maybe 20 kernel. I will start with buffer accessor, right?
Okay, thank you.
So I also have a question. So may I ask, is there any performance comparison between SQL and OpenCL and CUDA?
Oh, there are plenty. I mean, so we wrote a SQL bench, which is a benchmark for SQL only, SQL on different architecture. But I think what can be very interesting in terms of performance portability and comparison against CUDA, we have a couple of experience with industry projects. Well, one is a drug discovery platform. It's called Ligate. I can show you some publication. I can send you some specific publication. Another project I suggest you who did a very deep study on this is GROMACS, which is a molecular dynamics framework from KTH, and they had very, very good performance portability problem. I mean, right now, this is my feedback. For simple kernel, performance are if you compare CUDA versus SQL, performance are very, very similar. Plus, don't forget one thing. You have two compilers right now. So sometimes one compiler is more efficient than another one in the mapping. In particular, adaptive CPP maps directly to CUDA code. Okay, while one API goes through PTX and use the LLVM backend. Plus, sometimes you can target the same device using different backend. Okay, sometimes you have native backend and the SpearV, which is OpenCL-like backend. So if you test all the combination, you pretty much always find something that is very, very close to native. This is my experience. With very, very large code base, this can be more tricky, but there are at least right now, there are many groups doing this. I'm not even reporting what I did. Last supercomputing, there were many, many papers showing similar performance. So I think the standard is becoming more mature and implementation are getting closer and closer to native one. Of course, if there is a feature that only NVIDIA could has, this specific feature is not yet on the standard, of course, you may lose something there. But the standard as it is SQL 2020 right now, we have pretty much everything. We have subgroup, group algorithms. We can map any kind of synchronization. It's very, very, very. And what I saw is that really in the last few years there is a huge improvement in performance because of compiler maturity. This is, in my opinion, is very promising. I don't think you lose for most of the application. You should be between 10% slower using SQL versus CUDA, and sometimes you are really at the same level, unless you use very specific feature. Okay, this is my personal take. But I mean, really, there are, as of today, there are plenty of paper on this, and they are always getting better. Okay? And they're getting better and better. So this is very, I think, it's very, very interesting right now. You're welcome.
Any other questions?
Just a quick question. You said that we have to create a different queue for each GPU, right? Unless we use Celerity, for example, which supports.
Yeah, so just to be clear, Celerity is a research project, okay?
Okay.
Take it as it is. But yes, with
Okay.
Celerity has this capability, yeah.
Okay. And also moves data transparently across different nodes as it's needed.
Yeah,
Right.
correct.
So does it have like a unified address space across nodes in some sense? So how do I, for example, initialize data?
This question is specific to Celerity.
Yes.
Okay. So Celerity buffer is only supporting buffer accessor. So like you have buffer, buffer are abstract in SQL, they are abstract to the hardware in Celerity. Then when the runtime knows about the mapping, when does it know? When you have the accessor, then it does the mapping and does the distribution. So it's lazy in this case. Celerity has a trick, use a trick. It does a pre-execution of the graph only to build the graph and then later execute it. Okay. This is a trick that allows you to know the dependency in advance before you run it. Okay. And this works quite well for most code. Okay. Let me say, but let me say this is a research project, so it's not production ready as it is the core of SQL. We are comparing one API, which is industry maturity, with a more research project. Okay. But yes, it's capable to do it because of what I told you. So there is have a look to the runtime paper. It is written the details how this works. But the idea is that the task graph is pre-built and later executed. From the task graph, when you execute it, then it generates the command graph. But it is really enough to the runtime system to know those range mapper binded to the accessor to do the data movement.
Thank you.
You're welcome.
Any other questions? If not, I have a question for the speaker. So one of the most important things about supercomputers is that we need to be able to scale, right? So do you foresee for a project which is cross-compatible with respect to different hardwares like SQL or Celerity or whatnot to be possibly used as an orchestrator across different supercomputers to do some very, very heavy simulations or computations? Of course, we would have a lot of latency, a lot of time spent doing data movement, but could it work as an orchestrator across different supercomputers with different hardware?
But you are talking about SQL or Celerity, or I mean,
I
okay.
mean, SQL in general or one of
Okay.
its extensions.
I mean,
Do you foresee that happening?
yeah, I mean, orchestrators are really there are many workflow projects right now. They are like an independent piece of software using CUDA or SQL or whatever just as a backend. So it's just one more backend. So anything works in terms of orchestrator, it's just one more backend. So yes, it works, and I think it's really done because in this European project we run Liget, there is this workflow engine from IT4I. They do it. They do exactly this. There are many more projects from BSc on workflow. So I think they also support SQL. I'm not 100% sure, but it's perfectly doable if they haven't yet, because it's just one more backend. So yes, I think it works. The problem, of course, they must be supported also. It must be installed in the supercomputer, but it is also relatively simple to do.
Okay, so let's thank our speaker.
Thank you very much.